Eccoci all'osservatorio meteorologico qui, anche uno degli istituti più antichi a Davos.
We're sitting in the lowest part of the atmosphere that we're breathing in. But as you go further away from the atmosphere, towards the edge of space, if you like, towards the edge, the physics and the chemistry changes throughout. Those models can then be used to estimating and predicting what will happen in the future, depending on different scenarios. So if we stay on track with reducing the Earth's temperature, what will happen? If we don't, and countries don't work together, what will happen? So he wanted to understand why the atmosphere here was so good for patients with lung conditions. So he developed instruments to understand the atmosphere. Over the years it's become bigger and bigger, and in the 1970s it became the World Radiation Center, where we're hosting the world standard for radiation measurements from the sun. Countries around the world, governments, med offices, want to have the most accurate measurements around the world, and this is really key measurements for climate models, for solar energy companies, and they come here to have their instruments calibrated. We do a big calibration campaign every 5 years where everybody comes here.
Up here we measure the solar irradiance in different spectral regions and for different conclusions. So for example, this is our reference instrument for the infrared. So they are calibrated and has the true value, let's say.
Okay.
And then the other instrument comes here, they measure simultaneously, and then you compare. And then you give a calibration value. These domes are because all the instruments are heated, and you see there is some air blowing.
Ah, yeah.
Yes, so to keep them in a rather protected environment from the snow. So I'm just going to show you quickly the dark side of the measurements.
Yes. Dark side, I like
Yes. This is a laser that you can select whatever wavelength you like. So if you like to have green, then you have green. It is safe, but it's better that you wear this.
Yeah.
Here you send one wavelength, and then you measure here the response of the instrument.
The sun, we look in the sky and it looks like a white ball or a yellow ball, but it is actually a star that changes. It's a middle-aged star, but it varies on timescales from minutes to days to weeks to months to years. We need to understand that variability because that's a basic input to climate models. We also need to understand that variability because it creates activity that affects us here on Earth through the impact on technology. The most recent example was with Elon Musk's company launching more of his spacecraft, and he lost about 40 of those due to a solar storm. So that was back in February. So the sun's currently in a higher activity phase. Those timescales that it changes on are we understand to some extent, but we don't understand enough. We don't understand the trigger of a big explosion in the sun. We don't understand the cycles enough. Will the next cycle be much larger than this one? We still have a lot to learn. This spacecraft gets all the way as close as Mercury to the sun. So we're getting in close to the sun to try and understand that activity. And this movie is showing us data from January to March, and that was when we were getting to our closest point to do the very first proper science close point perihelion. So during this time, we can see a lot of activity. So the data you're seeing is measuring high energies on the sun. So it's about 1 million degrees. So really quite hot, quite different to what you see day to day. These images allow us to see something we cannot see by eye. And we choose the colours because for us, I know to look at that. That's the filter, that's 1 million degrees. But it was not a real colour at all.
What's the real color of the sun then?
So for us, when we're looking at it, we look in visible light, so it is sort of yellow.